In this talk, I'm going to take a complete small concurrent program and do some refactorings on it. I'm going to break it into two parts, one of which contains all the concurrency primitives, the other contains none of them. So I'll start with the program. This is a little counter program. It's about the simplest concurrent program you can write. It represents a counter. You can do two things to the counter. You can increment it by, you can call a function tick of n. It has a local state variable whose value is some value. If we say tick of n, it will increase that state variable by the value of n, and we can read it, and it starts off at 0. So it's a very simple thing. If we started it at 0 and said tick of 5 and read it, we'll get back the answer 5. If we then said tick of 10 and read it, we'll get back the answer 15. So it doesn't do anything complicated at all. And it's intentionally simple so that we can concentrate on the details of how it's been built. So it's put into one module. The module is called counter 0. That module exports a start function, a tick function, and a read function, and also a loop function. The loop function is not... It's really there for technical reasons, because when you spawn a function, if you use this spawn module function arguments syntax, you have to export the function which is being spawned, and that's why loop is being exported from the module. So to start the function, we use the register primitive, so register counter 0 as spawn counter 0 loop 0. And that makes a global process called counter 0, and it's running this function loop whose initial argument is 0. So if you look at the state, the value of state in the beginning is 0. Now to tick it, we do a remote procedure called tick of n, and that was the same remote procedure call that I showed you a couple of lectures ago, so I won't talk about that again. The message, the tick message gets received. It sends back an ACK message, an acknowledgement, and in the case of a read, it sends back the value of the state variable in the loop, and then it recurses with either state plus n if you sent it a tick n message, or it recurses with loop of state if you sent it a read message, because the state doesn't change if you merely read it. So that is just about the simplest concurrent program it's possible to write that actually does anything that's vaguely useful. So what I'm going to do now is factor it into two parts. I haven't changed the RPC function, so I'll leave that alone. But what I have done is move some of the code into a separate module, and the module that's called counter 0, the bulk of that code is now in a module called GenServerLite. It now exports a start function with two arguments. Loop is exported for the same reason as before, and I've put the remote procedure call into the GenServerLite module. Okay, so what does start of module state does? It registers now mod. If you looked at the last program, register was frozen, the frozen value counter 0. But in this case, it becomes a variable. In this program, mod is not an argument to start, but in the next program here, the module is the first argument to the start function. So we create a registered process, a global process called mod, and it's created by spawning GenServerLite loop mod state. And if you compare that to the last program, state, loop had one argument, which is state, and now it's got two arguments, mod and state. And that second argument, mod, is passed through all the calls to loop. Now there's only one pattern in the receive part of the code. And that says that, okay, so if we get from tag query, it's to evaluate mod : handle query state. So if that had been, when we start that, the value of mod is actually going to be counter 1. Okay, so it's actually at the point where it says mod : handle query state, it's going to call counter 1 handle query state. That's a function of two arguments that takes the message that the client has sent to it and the initial state, and it returns two values in a tuple. The first is something that's got to go back to the client, and the second is the thing you have to recurse with. And so the return value from mod handle query state is this tuple reply state 1. Reply goes back to the client. State 1 becomes the argument of loop for the next recursion. Okay, what about the code that calls it? Counter 1. Well, start, first of all, I say import from GenServer Lite start and RPC. That's all I need to do. And then I say, well, start is start of counter 1, 0. So it calls GenServer Lite mod state with the value of mod being counter 1. And then tick and end just become 2 remote procedure calls. And then I have to supply this handle routine that has 2 arguments. The message that has been sent, in this case, tick of n or read, and the state, and it returns 2 tuple with 2 values. One of the values is to go back to the client, the other is for the recursion. Okay, so I've done that refactoring. Now, if you look at that refactoring, you'll notice something interesting about it. I've split it into 2 modules. Now, one of the modules has the primitives register, spawn, send, receive. These are all the concurrency primitives. The second module, counter 1, has none of them. So what I've managed to do is split a single program that has concurrency constructs into 2 modules, one of which has all the concurrency parts. The second one has no concurrency parts at all. And that's good programming practice, because concurrent programming is actually rather difficult. And it's perceived as difficult. And in many cases, we don't need to write totally concurrent programs. We need to use concurrent frameworks. So we can take something like a server and turn it into 2 parts, one of which is generic and has the concurrency primitives in, the other of which is well-typed sequential code. Okay, so this is, I think, this is the road to the generic servers that live in the OTP system. We can do a lot more than these simple transformations. Both sides of this code can be developed separately. So you can have one group of people who take this GenServer Lite thing and improve it. They make a much more complicated one, and that becomes the GenServer in the OTP libraries. And Francesco is going to tell you more about that in his lectures. The second one can concentrate on the client side of things, and they don't really need to know how the gen servers work. They just need to use them. So we can separate the division of labor when we're building systems. It turns out that you don't actually need a very large number of generic things, but you do need a large number of plugins. So I've been involved in some very big projects where we've had 60 or 70 programmers, and the vast majority of them have been writing generic servers, things like that, with very few people concentrating on the generic parts, which can be used and reused by everybody. Okay, so to summarize, we saw earlier that Erlang has 4 primitives for concurrency: spawn, send, receive, and self. It's got a mechanism for timeouts, it's got register and where is, and it's got mechanisms for trapping errors. And we saw how to build our own concurrency abstraction, but we didn't see how we put the parts together. This example shows how we put the parts together. And by extension, it shows how we build libraries and frameworks that are useful for building much larger systems. And Erlang has been using these frameworks for building very large and very successful commercial real-time systems. And in the next lecture, I'm going to go into a little bit more detail. Not about that, but I'm going to build a model that is perhaps slightly more complicated and is approaching real systems. And then Francesco will take that up and turn it into production quality code.